Good afternoon, everyone. Thanks for joining to our today's Q-Farm seminar. I'm very glad that today we have Valentina Parigi from Laboratoire Kastler, Brossel, Sorbonne University of Paris, where she is an associate professor since 2015. So Valentina's research ranges from foundations of quantum mechanics to experimental implementations of quantum networks. She has won a number of awards, including the ERC grant and CNRS bronze medal. I'm very happy that she's with us today, and she telling us about her ongoing project on implementing complex networks, complex quantum networks in continuous variable settings. Before I hand it to Valentina, just a reminder to everyone that if you have questions, please feel free to post it on the chat box here, or unmute yourself and ask your questions. During the talk, Valentina is also willing to take questions. Okay, take it away, Valentina.
So thank you very much for the nice introduction. And well, first, good morning to everyone. And also, thank you for having me here. It's a great pleasure. It's a pity that I cannot be there in person. So I think it's nice also to have chat with person later on after the talk. So as we cannot have it, so please, if you just want to have a virtual coffee with me on chat later on, just please put it in the chat, or just send me a mail. It's going to be a pleasure for me. So yeah, as Vaid was saying, so today I'm going to speak about continuous variable quantum complex network. Is my current project that I lead in a group which is larger than my activities, including other activities, the multimode quantum optics group in Paris. So probably you see the first slide of my talk with a picture, which is a pre-pandemic picture where people could still gather together. There's two more people on the side that just arrived later last year, so that was too late for being all together. Well, let's say we are lucky enough that we can still gather in smaller groups in order to do experiment in the lab, which is very good for us. But yeah, we're missing a kind of large gathering situation like the one of the picture. So we start with the outline of my talk. So today I want to speak about quantum complex networks. I will start by defining what I mean, what is the definition that I'm going to use for quantum complex networks. That is a little bit different from just considering quantum communication or quantum information network. Of course, is very much related to them, but I iterated the definition more from complex network theory in general. Then I will speak about the special kind of quantum network that we built in multimode quantum optics, which are continuous variable cluster state. I will go very briefly on theory and our experimental implementation, and then I will explain why I think it's interesting to go complex in that regime. So normally cluster states have a regular structure, but I think it's good. There are good reasons for going complex too. And then at the end, I will speak about non-Gaussian classes. So non-Gaussian statistic is necessary to get some advantage in quantum computing. And what I'm going to speak about are mainly two different challenges. One is an experimental challenge, the fact that when you have large system, which is multi-mode, which is non-Gaussian, to have full characterization of it from experimental data is very hard to get full tomography of the quantum state. And the second benchmark is that this kind of system is also hard to, the second challenge is that this system is very hard to benchmark even theoretically when they start to be quite large. And I will show tools that use complex network theory for doing it. So, okay, very good. Let's start with the quantum complex network. So I will start by recalling complex network that are defined as all the network that are neither regular or random in network theory. And especially when I'm speaking about regular case, I'm mainly speaking about the fact that you have a deterministic rule for building them. While on the other side, the random network, you have just a bunch of nodes, and then, well, kind of probability for having link or connection or nodes between them. And then in between, you have something that has some particular rule, but still have kind of probabilistic rule inside. And this is what I call complex networks. So a complex network model has been introduced to describe real world network, like social network, chain of metabolic reaction, or even internet. And they are quite effective to get the statistical properties of real-world network, probability distribution to show kind of emergent behavior, giving small world and community structure, which correspond to particular functionalities like selection and resilience. Well, when I speak about quantum complex network, I'm thinking about this kind of model applied on the quantum world, meaning that I consider a quantum complex network a kind of structure in which I can identify nodes that are quantum system and link that could be physical interaction or entanglement link. I think that this network, this quantum complex network, interesting in general in quantum technologies, for example, for simulating behavior complex or quantum natural phenomena, and also to optimize kind of structure that are going to be used for quantum information and quantum communication protocol. This is exactly what I'm studying in my current project. So what are the nodes of my network? What are the systems that I'm considering? So I work with multimode quantum optics. So multimode optics just deal with different modality of light or propagating. So mode of light at orthonormal solution of classical Maxwell equation. And in particular, the one that I'm going to use are different spectral temporal shape. So the node of my network are going to be different temporal spectral modes. Then I work in the continuous variable regime of quantum optics, meaning that if I have to use one of the diagram to describe my quantum state, I'm going to use the one on the right, which includes the phase space. So for each optical field, I can define an harmonic oscillator, going quantum, and then using P and Q, so position and momentum quadrature, to describe my fields. And I'm going to encode the information on this variable. And in particular, when I speak about links between the nodes, I'm going to speak about correlation. So maybe I'm going to speak about entanglement, so kind of quantum correlation between the different nodes. Very good. Now I will come to the first example of quantum network that I'm going to consider today, which are the continuous variable cluster state. So cluster state in general, CVNDV have been introduced as a resource for measurement-based quantum computing. So these are the main resource that can be used in order to perform the computing. So they have a graphical representation, which is again with node and link. So the nodes, in the case of continuous variable, are different mode of lights, and the link had entanglement correlation. So in particular, if I just consider two of them, normally, well, you have to initialize theoretically this mode of light in an infinitely squeezed state along the pin quadrature, and then applying entangling operation concerning CZ gates. So of course, in real life, you cannot have infinite squeezed state of light. So normally you start with finite state of light, which is something they can produce in the lab, and again, apply this kind of correlation. So, and even more easily, this process is totally equivalent to have, if I just consider two nodes of the cluster, two different squeeze state of light that enter in a B-splitter. And at the output, we get what is the famous EPR state, which is very closely related to this two-node cluster. But exactly this state can exactly be obtained also by using parametric process, non-degenerate. So it has a linear optical process pumped at a certain frequency. You get two different fields, signal and hydra, to lower frequency. And in the condition where they are not degenerate, in particular here I'm considering two different frequency. Again, you get continuously, by measuring homodyne detection, correlation that corresponds exactly to the EPR states. Well, of course, if you want to go larger, in the meaning that you really want to build a cluster with many nodes, well, you need to have a bunch of squeeze state of light that in principle enter in a linear optic interferometer. And then at the output, you get exactly the correlation that you want, depending on the unitary that you apply, you get different kind of shape of your cluster, so different kind of correlation between different nodes at the output. And also, this can be done equivalently in a parametric process in which you enter with many different colors. So in particular, we use femtosecond pulse laser with a large spectrum that's produced in a parametric down conversion different colors and can be arranged in different entanglement connections. So in particular, if you look at what we produce in a particular basis, we have just a bunch of squeezed state of light. So normally, when we enter with a Gaussian spectrum for the pump, what we get as this basis is the Hermite-Gauche basis, the one in which actually the modes are totally independent, just squeezed. Then any other basis, which is a linear combination of them, you get entanglement. So meaning that by choosing the right basis, you can build the correlation that you want in order to get the cluster with a particular shape. In particular, we have also another way of getting the exact correlation between different modes, which is playing with the spectral shape of the pump. So actually, by these two different ways, one that I just call linear because it's just a basis change, a measurement basis, or by changing the spectral shape of the pump, you can build different kind of cluster by looking at the right combination of modes. So this has been done in our lab. So this is a paper of 2017, which we show that this kind of cluster state can be built in labs. So what you have, on the two picture on the upper part, you have the different shape that have been built, and then you have squeezing values. So exactly this is the squeezing of the nullifiers, which are actually operators, combination of quadrature of the different modes. That are supposed to get to zero, so to be squeezed, the variance is squeezed below the shot noise when you build a cluster with a particular shape. And this is, you see the case that actually the variance is below the shot noise. So what have been built in our lab are cluster up to 12 nodes. Well, of course, they are not really huge in terms of number of nodes. Yes, at first I have to show a picture that we do really experiments. So what I'm showing is not just a graph or of numbers, but this is a really experiment that have been done in the lab before and during the pandemic. Actually, see that we have masks. And then actually, yes, of course, we are not the only one, and also we are not the one able to produce the largest clusters in the world. So see, there is a lot of, well, let's say, kind of competition. So in particular, the largest one and being built by using temporal modes, kind of time-being configuration, in which you have different temporal mode corresponding to the lifetime of optical parametric oscillator cavities. And then you can entangle these different modes via the ley line and beam splitters. And so the two cluster, the largest one is the one that has been built in Japan, in the Furusawa's group. Then you have the experiment in Copenhagen. And then the largest one has been built in the frequency domain. This has been built by Olivier Pfister, University of Virginia. So what is interesting with our strategy is that it's quite easy to reconfigure the shape of the cluster that we have, meaning that I can think also to go beyond regular cluster and have particular kind of complex structure. And I will explain later on why I think this is interesting. Of course, we would like also to go larger. So this is something that we are pursuing. And in particular, we would like to merge the strategy that involves kind of time-being modes, temporal mode, and spectral modes of light. So in our case, our time-being, as we use pulse laser, is really the pulse basis. So meaning that what we are building are a single pass multimode squeezing source, so are not optical parametric oscillator, because normally when you add a cavity around your process, well, of course, your cavity is like a filter, so you're lowering actually the repetition rate at which you can generate squeezing that is going to be well longer than the repetition rate of our laser. But of course, as we still have, I mean, femtosecond layers are larger spectrum, we can produce for each of these time being different frequency optical spectra that are that have squeezing. So in a way, we are kind of multiplexing on the frequency and the time domain, the kind of multimode quantum resource that we are producing. And well, we just started to have some results very recently in the lab by using periodically polled KTP waveguide. And well, these preliminary results are quite encouraging in the sense that we measure something like around 14 squeeze modes, while the squeezing is still quite low for the moment, 0.6 dB. But this is really at the level of the single pulse. So we are able to measure the single pulse level, 14 modes for this waveguide. So this is very encouraging for getting larger number of modes in order to build larger cluster. Very good. So then I want just to briefly explain why already in this cluster cases where that are Gaussian state of light, but that can be deterministically generated in our case, can be nice to go towards complex shape. So why they're interesting? So they're interesting because, generally speaking, this kind of system can be structured as a complex environment. So in an open quantum system scenario, you can use this system to simulate kind of environment which is attached to another quantum system. So as probably you know, the effect of this environment can be pictured by using the spectral, what is called the spectral density environmental coupling. So just give the channel different frequency of dissipation of the quantum system in your environment, and very much characterize what is going on actually. So on the left side, you have two different kind of environments that are already kind of complex network structure. So this one is a Watt-Strogatz, is a model used for having a small world network. And this one is really a network that comes from it's a biological one from a cerebral cortex actually that we were trying to simulate, just let's say just for fun, but it is nice to get this kind of picture from the real world. And you can see that, so the blue line is the theory that give you the expected spectral density, while the different dots are different numerical simulation by considering different parameters of our system, the experimental one. So of course there is not yet experiment, so the experiment is going on. This is a model, but it seems that actually our system is quite versatile if you want to simulate actually the effect of different environments on another quantum system. Also very briefly, I want to say that well, of course, this complex cluster can be considered for quantum communication protocol in CV network, and it can be used to study entanglement concentration in quantum muting. So at first, of course, you can think about if you want to build this kind of complex cluster from experimental resource with a well-defined resource of squeeze mode of light, what you can do. So normally you can apply kind of linear optic transformation, and you can try to optimize in order to get the best entanglement connection, meaning the best nullifier. And so we try to work a little bit on it. And I mean, still you can see that even if you can optimize the complex cluster, the regular are better to let's say, optimize. Then, of course, you want to use for some kind of protocol. So the idea that I have in mind that, well, in CV, continuous variable case, it's quite easy to prepare a bunch of multimode systems that are entangled in a deterministic way. So then you can distribute, of course, I'm mainly thinking about short range kind of network between different so here Alice and Bob. And then you can try to rearrange the network given the kind of task that you want to do. So this is very, what is shown here is a very simple one. Just you want to have a two-mode channel between Alice and Bob. And the idea is just try to do it in a most simple way, in quantum optics, meaning linear optics transformation. Can you always do it? So the answer is depends. And the idea is just we try to test some particular shape by sharing different nodes between Alice and Bob. And I mean, not always you are able to accomplish this task. So this has been done via numerical calculation. So there is no analytical way of solving this problem, at least not known by us. And actually, of course, these are preliminary results. We are working on a complex network shape, because what is really interesting that imagine that you want to build kind of cluster that has the same shape of internet, of bunch of internet connection. Is going to be this really the one that is easy to reconfigure in this kind of situation in which you share the link between two or maybe 3 or 4 different players. So this was very briefly to tell you how I think that complex cluster could be interesting in different tasks, let's say, or different problems in general in quantum technologies. And then I'm going to go to the, let's say, the main part, which is speaking about non-Gaussian cluster. So, of course, it's well known that if we just say with Gaussian statistics of quadrature, is very hard to get in something that is interesting for quantum protocol, because I mean, Gaussian state of light can be, or Gaussian state in general, not only of light, can be easily simulated from a classical computer, even very large. So there, you need some non-Gaussianity in order to see some kind of quantum advantage. So the way we tackle non-Gaussianity in our laboratory is to use probabilistic process. So up to now, I mean, the generation of my cluster has been a deterministic process with many modes. Could be, well, in the temporal domain, I forgot to say, but you can arrive to something like 10 to the 6 modes that are entangled. So million of modes that can be used for your protocol. The non-Gaussian part is introduced with probabilistic protocols. So for example, it's not the only one, but the one that has been mostly explored in our laboratory is the single photon subtraction that we have to do in a mode dependent way. So meaning if you think about your cluster structure, you want to be able to select one particular node of the cluster that I recall is just one particular mode of light. So here, what we do is to merge the quantum states with a coherent state that we call gate on a nonlinear crystal gate by doing some frequency conversion. So every time that we see a single photon coming out at the some frequency, we know that we have lost a photon from the signal. And in particular, this process can be engineered in a way that the shape of the spectral shape of the gate is able to select the spectral shape from which I subtract the photon, so the mode from which I subtract the photon. And so this has been done in the lab. So here what I'm showing is, well, the signal entering, and I'm showing it in a particular basis in which is diagonal, as I was saying before. So in the sense that I have just a bunch of squeeze mode of light, which for us is the mode basis, which is the spectral Hermite-Gauss basis. And then you have, so at the output, so on the right corner, you have experimental data in the sense that you have quadrature data and experimentally reconstructed Wigner function for this state of light. And this is with no events in the sum frequency conversion. If you just send one particular mode, here for example is AG1 mode, and we detect a photon, what you get by just looking at the different modes via homodynamic detection is that the AG1 mode, I mean, has become non-Gaussian, and in particular have negative Wigner function. So this can be done also for the other modes. This is nice, and of course it's nice also if you can subtract a photon from one corner of a cluster. So here's just a square cluster. So remember, I mean, the way we build cluster is via basis change, meaning that this cluster has different nodes, and the node is just a combination of modes that are defined in my diagonal basis. So if I want to subtract a photon from these nodes, I have to send as a gate field exactly this mode, the one that define my my nodes. This is what have been done. And so what you see is the results for homodynamic detection in the different nodes, which correspond to different modes. And well, you can try to access the excess kurtosis from this distribution. And here we have two things. So the first is that, well, it's not easy to see from the distribution. You can see from the excess kurtosis, but the node that is mostly affected by photon subtraction is not the node from which we subtract the photon, but this is the opposite on the other corner. So we start to see that, well, probably, yeah, looking at what is going on in cluster structure for this non-Gaussian operation has to be looked at a little bit in terms of what is going on in terms of shape, how a different shape can affect the subtraction process. The second point is that you don't see Wigner function. So actually, well, in particular here, if you really want to have the Wigner function of the state, you should reconstruct a 4-mode Wigner function, the global one. Which if you try to do it with standard methods that involves maximal likelihood process from optical state tomography, well, it's too hard to handle. So it's not really possible. So here I come to the two different challenges that we have for multi-mode non-Gaussian state of light. So the first one is really experimental one. So how to characterize this state when it start to be larger. And actually here larger is larger than 4. With normal quantum optics tools, I mean, quantum optical tomography, maximum likelihood estimation, already 4 modes is a little bit hard to do. The second challenge is that, well, these states, if you start to have many modes, so here I'm speaking about theory and many non-Gaussian operation, like single photon addition and single photon subtraction that you can do in many different corners. Well, this is exactly a scenario in which, I mean, has been proven hardness of continuous variable sampling. Even not going so far, well, being an intermediate regime, try to have a characterization of properties of these multimode non-Gaussian states is a little bit hard. And so what we have been doing is to work on this side by using a little bit complex network theory. So I will start at first by speaking about the detection of Wigner negativity in a multimode cluster, so which is the experimental challenge that I was studying as first. So this has been a collaboration between our group and the group in Roma-3. So here you have different persons that have been involved in this group. So the really driving force has been Valeria Cini, that really did the main part of the work. So actually, maximal likelihood algorithm, as I'm saying, I mean, computationally too heavy to be solved for 4 modes. So the idea is to ask to artificial neural network. Well, we are not the first one using artificial neural network. There have been many used already, even for quantum state tomography and also optical homodynamic tomography, meaning that you really want to encode in the neural network amplitude and phase of your let's say cat-based state. Is not the thing that we are going to do. So what we really do is to solve kind of binary problem. So injecting statistical data and ask if we have negative Wigner function. So we want to use, I mean, kind of the neural network in a binary problem, which is kind of very standard one. So what is the setting? So what we are doing is to generate any multimode states up to 10 modes. Meaning that any cluster, we fix the squeezing value in the beginning, and then we can generate any kind of entanglement correlation between these 10 nodes. Then we decide either if you want to subtract a photon from a bunch of nodes, which can be also from a combination of nodes, or we want to subtract, to add a photon, or we can also just do nothing. So stay with a Gaussian state. Then, I mean, let's say theoretical protocol, include the fact that you measure statistic for 10 different modes that are not exactly the one that define the cluster structure. It could be any combination of nodes. And then you measure according to 3 different value phase, so 3 different quadrature, and you acquire 1000 data. And then you repeat it for 1,000 times. Then actually the data are fit in 15 different bins, meaning that what we are feeding is frequency of occurrence on particular value of continuous variable, because here we are dealing with continuous variables, so we bin the value, and to the neural network. Then we have 3 hidden layers, and then we just ask the question, so the Wigner is negative or not? And the network answer. So actually what we do, up to this point, we can still generate training data. So this is, really the main point of our method, that we are able to generate a large enough amount of training data for which we can have analytical expression for the minimum value of Wigner function. And when we use a cross-validation procedure, meaning that we feed the data, and then we use 80% of the data as a training set, and then 20% of the data as a validation set. And here you have the results in the case where we are considering a case of 3-mode, 5-mode, 10-mode state. And these are, the results that are published in the paper. So for the 3 modes, we can go up to 95% validation accuracy. For the 10 modes, in the paper, we had only 0.85. Actually, we recently discovered that if you're playing a little bit with the binning, we can go up to 95 even for the 10 modes. And so this is interesting. The other thing that's interesting also is that something that is not in the paper is that we just recently discovered that this is robust, even if we train with a class of states and then we test different classes. So if we train with subtract and squeeze state, and then we test for Fock states, 1, 2, 3 Fock states, the neural network is still able to recognize the Wigner function is negative or not. So it seems to be quite robust. Also because actually what would be nice to do in the future is that you want to train, for example, for 10 modes, and then if you're able to get a system with 100 modes, we just want to ask the neural network, if the Wigner function is negative or not, without the need of training with a network, theoretical data that concern a very large network that needs time to be generated actually. So actually we did a comparison, for example, in the 3 modes case where we can still get maximum likelihood estimation. So meaning that maximum likelihood really do the full tomography of the state. And actually, if you compare, what is interesting that is our method is less accurate. If you really can give a lot of data, of course, the maximum likelihood method is more accurate, really reconstructs totally the state. But as far as you go in lower number of data, the neural network method win. Actually, this is actually exactly the place where we want to go, in the sense that we don't want to make many measurements in the experimental setup. So this is really interesting, actually, that it seems to be quite robust, and also, really allows us not to use too many data. So this is, and still work that is in progress, because we want to see how far we can go and really how we can implement it in the lab. Actually, in the paper we have the really experimental part that concern just 2 modes, because it's what we had at the time as data to test, but we really want to test this method in large number of modes. Very good. So I'm coming to the last part that concerns the benchmarking of complex non-Gaussian cluster via network theory. So as I was telling before, well, this kind of system in which you can add many different, single photon addition, single photon subtraction is not easy to benchmark. So if you have few number of modes and few number of operation, you have theories. What we have been developing in our group in the last 2-3 years. We have analytical calculation. We can have some kind of brute force calculation. But at a certain point, it's hard to get full images of what is going on with this quantum state. What we did is in collaboration with Nicole Karn and Bhuvanesh Sundar, that both at the beginning in Colorado School of Mines, and also now Bhuvanesh is in Gila. And it's a kind of method that uses tools, really the tools of complex network theory. So I want to go to the general setting and then to come a little bit back in general to property of also cluster state. So we, at the beginning, we build a theoretical cluster state. So in the sense that we consider what we call the imprinted network. So we have a bunch of nodes and we imprint particular network shape. So if you look at correlation that you have different nodes, is known that, I mean, they don't stop just in the nearest neighbor nodes, but you have to go up to the second nearest neighbor node. Meaning that actually the graphical structure just tell you where you have applied your CZ gates, but you have correlation up to the second neighbor. This is known. And then if you just have one photon subtraction from one node, well, you can have some kind of strange property like the one that was shown before, in the sense that you get some negativity or entanglement change on the other corner, for example, but you don't really go so far actually in terms of effect. As I mean, the correlation of the cluster are built in order to be short range, you just affect this network up to the second nearest neighbor. So this is true for example, for entanglement and Wigner negativity. But the question is, what is going on if one, you use as initial cluster state, one that has a complex shape. And second, what you want to consider are correlation between the different nodes. So not only the local quantity like entanglement, negativity is affected, but how correlation between different nodes are affected by this operation. So what we did is to build a complex cluster from the beginning. So meaning that we consider graphical structure with an imprinted network of 100 nodes and then CZ gates that can take a complex network shape. And then we look at what we call the emergent network. So the emergent network means that we look at different quantities that are photon number correlation. So we build this network by looking at photon number correlation 2 by 2 in the nodes. Why we have chosen it actually is because these are 2-point correlation that in principle can be measured, so they're observable, and quantum optic experiment can be measured. 2, because they contain up to the 4th order moments in quadrature statistics, meaning that we can see a deviation from Gaussian statistics, because really here we want to see what is going on in the non-Gaussian part of the states. So we start by looking already at the emergent network of photon number correlation before any photon subtraction. So this is the case, I mean, just take this structure of CZ gates, and then I build the network of photon number correlation, which is the emergent network. This is property that emerge from the imprinted network. And you already see that you have, well, it's a little bit tiny, but probably you can see that you have some more correlation, because I mean, this is normal, because I mean, correlation go up to the 2nd order, I mean, class. This is second nearest neighbor. And then we start to subtract photons. I actually decided at the beginning to subtract 10 photons from the same nodes. And well, you see that the kind of correlation structure is really changing. So this is the photon number correlation emergent network after I have subtract 10 photons from the cluster that I have at the beginning, which is this one. And well, the idea is that you want to look at it a bit at the statistics. Well, we did it for given a particular setting for the complex network shape, meaning that we define, for example, here is the complex network shape that corresponds to Watt-Strogatz network. This is the model for a small board network. So normally it's built by starting with a regular network in which you have a certain degree. You have, I mean, any node is connected to a fixed number of nodes. And then you start to rewire with a certain probability. And if you rewire more, you get more randomness. So it starts to be a more and more random network. And this is something in between. And then, well, if you want to collect statistics, try to see what is going on, you can look at a network measure. So we actually repeated 10 times with the same, 100 times with the same model. And then we look at the degree, so the number of link per nodes and the clustering. So these are quantity that are not just 0 and 1, because I remember that these A, I, J are the, the link that correspond to my emergent network that have been defined as number, correlation between photon number. So this is what I have been defining before. And this can take value from 0, takes value from 0 to 1. Continuous value, while actually the adjacency matrix of the classes just contains 0, 1 if you apply or not apply CZ gate. And actually, when you look at the degree and the clustering distribution, well, you see the following. Actually, what you have is that the degree distribution for the Gaussian case, the emergent network is already changing from the initial degree distribution for the Watt-Stochastic network, but that is really changing. So you have a second bound, for example, here for this network in the non-Gaussian case. And well, what you can say is that probably this part of the statistics come from the nodes that are really close to the nodes from which you subtract a photon. And this, well, you can try to break up the statistic by looking at different group that corresponds to different distances from the photon subtracting nodes. And then it's true that nodes at distance 1 has a strong impact on this second bump. Then this is changing statistics, but not all of them. So I have a little part here that didn't change. And of course, you also have some part of the nodes at distance 2 that gives you some contribution. So how this can be understood? So actually, well, then you have to go a little bit into the structure. What we were able to understand is really the structure of the subgraph at distance 1 from the photon subtracting point. So this subgraph, you can really see that the statistic breaks in different groups, which depends on the connectivity of the nodes. So if the nodes has no more connection apart from the nodes which the photon is subtracted, if it's so close, it doesn't change so much actually the statistics. While if you get more and more connection, the subgraph, while you get more and more effect on the degree, and this is the same also for the clustering. This is also, it's interesting because you see that the fine structure of the environment around the photon subtracting nodes is exactly one that is driving actually the changing in this graph. And also this explains why we didn't see a so large effect when we are considering tree graph. So this can be built as Barabasi-Albert network, and with n equal 1. And actually in tree graph, you always have kind of, triplets without the third connection, and meaning that you have a lot of nodes that are just connected to another nodes. And this is why we're looking from Gaussian to non-Gaussian case, and you subtract from the, especially when you subtract from the most connected, highest connected nodes, you don't see so much difference. While actually, well, I'm at the end, I'm just giving the very last point here. So we see differences in different networks. So the Watt-Stochastic, for example, the tree picture that I'm showing here is the degree distribution for the emergent network. When you change the randomness, in the sense that here what you change is the reviving probability from the regular network that you start from forbidding the Watt-Stochastic network, and you see that you have more and more effect for larger randomness. Also, in the Barabasi-Albert network, which is another model that's been built, especially to recover kind of power law distribution in the degree distribution, which is exactly the one that you find in real network, real world complex network. Well, here you see if you subtract from the highest connectivity node, so the one that has the maximum degree at the beginning, and you subtract from a random node, you totally find different situation. Well, actually, you have less effect when you subtract from the most connected node, which seems to be a little bit counterintuitive. But in a way, well, photon subtraction is kind of, let's say, correlation distillation, entanglement distillation protocol. And in a way, you are just diluting your distillation of entanglement, which creates correlation that can be seen also as kind of photon number correlation between many modes when you really select the icosnetted mode, which is not the case when you just take one random. So you change more when you take one random, because you are more, in the sense, you change more the value of the degree, which correspond actually to the correlation, because you're just affecting one or two nodes. So you see that actually the fine structure, what is going on, really depends on the complex structure. So just to come to the end on this part, actually, we can see that when we have a regular network, regular cluster, photon subtraction doesn't really affect so much the structure of correlation. While for complex networks, this is not the case. And this is also because you have a largest number of networks that are close, in the sense that, I mean, the mean distance in complex network is shorter than the one that you have in regular network. Also, actually, the amount of randomness in homogeneity counts of the number of link counts. So we have different effects if you have actually more or less random in the Vas-Strogatz network, or we pick up the hub that is highly connected in the Barabasi-Albert network, or we pick out a random node. And then, well, of course, we have a general behavior, because if you look at the bulk of the distribution, meaning the mean value and the variance, well, they are more or less affected in the same way for the different kind of network, but the fine structure, especially the structure in detail, really depends on the structure of the network. And then, of course, we have seen that there is a very important I mean, point in the local structure in the vicinity of network. So you can see that is graph at one distance from the subtraction point. We can really see how, I mean, the connectivity of the different nodes affect differently the statistic of the non-Gaussianity of the network. And I think I'm just coming at the end, and I'm thanking for your attention.
Thank you very much, Valentina, for the very nice talk. I'm going to do a random virtual plot.
Thank you.
Okay, we have time for questions. Maybe I can, okay. Kevin Multani has a question, actually. Kevin is asking, hi, Valentina, thanks for the talk. Is it possible to go from regular cluster to a complex cluster, for example, by removing the link or a node? If yes, is the transition smooth or sharp?
This is a very nice question, actually. Well, there are two things, actually. So at first, let's say that when you remove nodes, at the end, you have less nodes that you can use for your computations. So this is something that at the beginning we didn't consider. So in the sense that as we want to being able to reuse later on the network, we try just to reshape the network in order to get the right connection. And this can be done quite smoothly, let's say, with linear optics transformation. So you don't lose the information. But of course, I mean, if you don't arrive to what you want in general, we are mainly studying it for the kind of quantum routing protocol, but I mean, can be also recast in what you're asking, actually, yes. You can add measurements. And in particular, you can define two particular kind of measurements. One is the node removal, and the other one is the Y shortening that corresponds to measuring different quadrature on one node. One corresponds to the Q, other to the P. I'm not sure that is the right, which one corresponds to which one. But these are the two measurements that you can do. And of course, yes, you can do. We didn't really try to start from a regular cluster and getting a particular procedure for going complex that way. I think, well, in theory can be recast. It's not so far from the kind of quantum routing protocol that we are looking at. But of course, you reduce the size of your cluster. So it depends what you want to do, meaning that if you want to fix actually the size of the complex cluster that you want to have, and well, you have to carefully think about how large should be the one that's from where you want to start with, in order to but then transition is smooth or sharp. Yeah, it depends what you mean. I mean, for me, it's quite sharp in the sense that you're losing nodes.
Okay, thank you. Also, feel free to unmute yourself and ask questions, but I'm going to ask quick questions. So, like experimentally, I was wondering what's the, how much flexibility, going back again to the graph states generation and detection, how much flexibility you have to generate basically any arbitrary form of graphs.
Well, when you stay Gaussian and you just want to generate the states, actually, I mean, we're really flexible in the sense that in principle you can get any shape. Then, of course, then, I mean, you can ask about the quality of the state that you want to get. So this is, for example, what I was trying to speak a little bit about here. So for example, you start from a bunch of squeeze state of light. And so in principle, you would like to have all the same level of squeezing. You would like to have a large value of squeezing is not what you get. And normally you get kind of different spectrum of squeezing. And then you can try giving this spectrum of squeezing, well, you can apply linear optic transformation and well, actually have a degree of freedom that you can use in order to optimize, for example, the quality of the class that you get. Meaning that normally what you try, it depends what you want to do, but for normally if you want to use it for quantum information protocol, what you want to optimize is the squeezing of the nullifiers. So that really define the good entanglement correlation that you get. And as I was saying, actually, it seems that when you start from experimental condition, well, you have kind of spectrum of squeezing that is not flat, is still easier to, for, I think, just geometrical properties, easier to I mean, let's say optimized regular than the other one. Then, well, of course, depends what you want to do with this cluster. But in principle, if you are all the degree of freedom from the beginning, you can build any shape. And then, of course, if you want also to, for example, to play a little bit with the level of squeezing, the kind of mode that define your class and so on, you can also play with the spectrum of the pump. But this is a nonlinear problem. In the sense, for example, if you want to get some particular results, we use again a kind of machine, well, it's not really a machine learning technique, it's a, well, it's a genetic algorithm, evolutionary algorithm kind of problem, which you go in your parameter space and you try to get exactly, by changing the shape of the pump, you try to get the results at the output that you want. And in principle, this is hard to say if you can do it, in the sense that normally you find some solution that give some very, well, complex spectral shape that probably you cannot do in the lab, or yes, but it's very hard to say that there's only one univoque solution to this problem. So.
Okay, okay. Thank you. Any other questions? Comments? Okay, I'm going to ask one more question. You were showing the experiment that I think it was about like your experiment that you're combining frequency modes and time modes, and very recent result that you said you're showing 14 modes or perhaps or so. I was just wondering what are the limits from in the number of modes you can achieve there?
It's a very, very good question, actually. Yeah, it depends. So theoretically, from this experiment, so I don't get actually the numerical situation, but you can simulation, but you can get something like 100 modes that are squeezed. The problem is that you have to be able to detect these modes. And so, for example, if we stay with the Gaussian pump at the beginning, meaning that we get squeezing in the bit Gaussian basis, as far as you go, I mean, Eiger number or Eiger index of the modes, you get a larger spectral shape. Meaning that if you want to detect with a local oscillator, you need a larger local oscillator. So of course you can play in the lab by try to, with nice, I mean, nonlinear processes in order to broaden your local oscillator, which is something that we're looking at and we're doing so on. But I mean, you cannot really get everything. well, in a way, you can play a little bit with the degree of freedom also that you have in the nonlinear optical process. So actually, especially, I mean, this paper that I'm citing here, we are looking at different condition. So this is particularly is for an experiment that we are, so it's the theory that for experiment that we are bidding a telecom wavelength. And you can play with, well, in a nonlinear waveguide, you have the polling, you have the size, you have a lot of parameters that you can play with. Again, this is again the nonlinear optical process. So you can get numerical situation and simulation try to optimize the kind of condition you get. You cannot get everything out of it. No, normally, I mean, you can get a large number of modes, but probably few squeeze per mode, but you can get kind of modes in which that are able, you can measure and so on. You know, I mean, it's kind of a large space for degree of freedom that you can play with. We really think that we can go beyond. So, I mean, for sure we have more than 14. Also here you see that we have squeezing value that is not so large. That probably depends also on experimental imperfection, on the kind of homodynamic detection and other stuff. And that, so probably we should see more and a larger squeezing value. But yeah, but in the engineering parts, there is still work to do in order to get the best. But this is, I mean, really something that's, I mean, imagine that you have 14 modes, and they, I mean, this next step is to entangle the 1,000 time being, or I mean, the 1 million time being. Well, it's quite large class that you can get from it.
Yeah, that would be very interesting. Okay, Kevin is asking another question. He's asking, what are the main challenges in the multimode detection scheme? I guess I'm just going to also add another comment on that. So this goes kind of like between the competition, perhaps you mentioned, between the frequency multiplexing or time multiplexing. In frequency, perhaps encoding is a bit harder to detect than a large number of modes. I was wondering about if you can comment on that.
Yeah, I mean, actually, you have different challenges in the two different detections. For example, actually, here, well, let's say, I mean, for us here, as we really wanted to be fast, in the sense, I mean, the scheme that has been implemented so far, I mean, the repetition rate of the state itself, that depends on the time of the OPO cavity, is less than 10 megahertz. So here we are, I mean, especially in this experiment, 150 megahertz. So having homodynamic detection, which is, I mean, efficient to over a large bandwidth. I mean, this has been a work of 3 years for our PhD students in order to get the right results. And then when you detect in this time being scheme, of course, all your modes do not exist at the same time in your table. But actually, you have this kind of, multi-rail structure that you keep measuring and you keep giving feedback to the modes that are coming and so on. So normally in the frequency basis, all the modes are there at the same time. So I mean, you can use simultaneously if you want, and you can really send on the different provider. Of course, I mean, the detection scheme is quite versatile in the sense that for us, we can really select via pulse shaping, femtosecond pulse shaping, any modes. That this corresponds to any kind of linear optic transformation. But with this detection, the pulse shaping detection, we cannot select all the modes at the same time. So we can just address in a cluster, for example, node by node.
Yep.
We can, I mean, depict any class and so on. Then there is one particular basis in which you can do it, which is the frequency basis, because there, to separate the different frequency is easier because it's just a dispersion element. And we have what we call a multi-pixel detector there. But then you fix the basis that you want to work with. Mm-hmm. But then actually you have the other degree of freedom, that is the pump shaping, if you want to build the cluster. So this start to be nice. And actually this is, I mean, even nice if you can think about something like a multiplexed scenario in which, so I was saying that we are building a telecom wavelength source in which you really want to use the multiplexer in order to send the different, let's say, slice of frequency to different providers. This could be a nice point of view. Of course, if you just want to stay without pump shaping and just being able to select from the detection any mode. This is hard if you want to do it simultaneously, because you need something which is a mode sorter. And a mode sorter in different shape is a nonlinear process. So it's a little bit harder to address.
Yep. Okay, thank you. I'm gonna actually stop the recording since we're at the top of the hour, but we can stay on if there are more questions and discuss.